Okay, so I'm going to start the F block elements today. What do you believe the F block elements as the inner orbitals? Inner transition elements. Okay, they are also called as inner transition elements because they are generated from the transition elements and they are situated at the bottom of the periodic table. So we call them as the inner transition elements. F block elements we have. So basically in the D block, we have two elements, that is the lanthanide and the actinoid. So those actinoid and lanthanide, the lanthanum and actinum, we call it as. So they make their separate group, 14 elements group, because of their different property, different chemical properties, physical properties. They are arranged at the bottom. Hridaya, just give me a minute. Huh?
Yes, ma'am.
Hello. Good morning, ma'am. Good morning, ma'am. Yeah. Yeah, ma'am. Yes, ma'am. Yes, ma'am. Not yet, ma'am. Afternoon, I'm going to call him. Okay. Uh-huh. Okay. Yes, ma'am. Sure. Yeah. Yes, ma'am. Sure. Thank you. Yeah. See you, ma'am. Ma'am, any documents do I need to carry for yesterday? Huh. Okay. Bank details of the last employer, na? Okay. That. Mm-hmm. Okay. Okay. The documents which you have given in that, right? Yes. Yeah. I'll carry all those. Yes, ma'am. Yes, ma'am. See you, ma'am. See you tomorrow. Thank you. Bye-bye. Okay, so Hridaya will start inner transition elements over here as I spoke to you about the two elements in this lanthanide and actinoid make their separate group and they are called as a lanthanide group and the actinoid group. So what these 14 elements after the lanthanum, we have a specific characteristic. We are going to talk on that. Okay. So they are basically having a separate nature, or I would say the different characteristics they hold, and due to which they are kept in a inner transition elements group. Okay, that holds, each group holds the 14 elements with it. Okay, Hridaya, any difficulty in understanding this?
No, ma'am.
Okay, Hridaya. So we have the F block elements, and why do we call F block? Listen, the reason why do we call it as a F block, because last electron will enter into F shell, right? So F shell we call as the penultimate, it is called as the penultimate shell. Yesterday we had a question, like day before yesterday, when while studying the D block elements, we had a question, what do you mean by the no why the electrons are so n-1 d we had there. Now here what will be called as the penultimate shell here, n-2 for F orbital. So the element will be going into n-1 df. It means if you have n value 4, so according to this, what will be, or 5, because that does not have in a fourth groups element. Na? So element actually in a lanthanum and actinum, they have in a period 6 and they belong to period 6 and 7th, right? So if they are 6, it means 6 minus 2 NF. So this will be 4F, right? So this is called the anti-penultimate subshell. What do you call this group as? Anti-penultimate shell. So this enters into that, I would say, just a minute. So enters into n minus 1 2 f subshells, that is called anti-penultimate subshells, and electrons, since entering into F cell, we are calling them as the F shell or F block orbitals. So we have basically lanthanide series named as 4F series and actinoid series named as 5F series. Clear? Clear? So we say lanthanides are F 4F series. So did you understand the meaning of 4F? 4F means n minus 2, right? 6 minus 2, it will be 4F. And the second is actinides. Okay, the second is actinides. So we said this series is also, we have one, right, extra seventh, so that will be the 5F. 7 minus 2 will be 5F series. So they are called as 4F series and 5F. So there are total 14 elements. Lanthanum also contains the 14, actinum also contains the total 14. So they make a series that's called lanthanide series and actinide series. Did you understand? Now here we'll learn about the general electronic configuration as we have learned in the previous. Same way, we are going to learn the first general electronic configuration, how to write. So general electronic configuration follow this sequence, goes in order n minus 1 2, okay, f 1 to 14, because f can hold maximum 14, then n minus 1 d 0 to 1 and ns 2. This is the general electronic configuration for the F block elements. Before we mention the noble gas, okay. So for example, if you are having lanthanide series, for lanthanide what we can say, it will be noble gas. What is the noble gas? Previous xenon. Okay, before that xenon is present. 4f, the elements will hold 4 in f orbital, 1 to 14 electrons, right? 5d may 0 to 1 and 6 may completely 2 electrons. So this electron distribution is based on n plus l rule. So if you look at over here, 6s ke liye if you count, this is the n value, this is the l value. S, L value will be 0. If it is P, then L value 1. If it is D, L value is 3. So 6 plus 0, what is the value? 6. 5D, similarly calculate for 5D. 5 is N, D is L. So if L is equal, D is there, then L is equal to 2. Got it? So 5 plus 2 is equal to 7. Then 4F, 4F may N plus L rule will apply. This is N, this is L. So L is equal to 3, 0, 1, we go in this order 3, S, P, D, and F. Got it? So 4F may, you can say 4 plus 3. What is the value? 7. Then what other thing can, because here we are having both 7 numbers. So what else we can have other differentiation? So let me tell you here, since both are having the n plus L value same, so we will go for n value now, just n value, because both are having n plus L value same. So we will be considering n value just. So what is the n value between least n value between 4f and 5d? It is 4f. So the 4f, since it's the least one, electron enters into that first, and then remaining electrons will enter into the 5. Okay, did you understand? This is how the distribution will take place. So the general goes in the xenon and 4f 1 to 14, 5d 0 to 1, 6s2. This is how it goes. Okay, right? Any doubt?
No.
Okay, so I hope this electronic configuration is not a difficult part, right? Now, let me tell what will be the most common oxidation state of lanthanoid, right? I will share the all from the all 14, like 14 elements ka electrons, how it will be distributed. But generally you can take this as the configuration. Okay, now let us talk the next characteristic oxidation state after the electronic configuration. Oxidation state, Oxidation state, what type of in the previous you have seen variable lanthanoid, most common, what most common oxidation state seen in this is OS, means oxidation state, okay, of lanthanide. La means lanthanoid is +3, okay. So some you can say the lanthanoid when we are writing, right? So we will be taking complete in a form of ln, right? So this is how we represent the abbreviation form of the series. Okay, so here we go with this lanthanoids. Most common oxidation state is +3. Okay, but one compound, like I would say cerium. Cerium is the one which will show +4. Cerium is the one which will show +4. Okay. Then when we go for the other element, yttrium, this will show the +2. These are the element comes under the lanthanoid series, 14 elements in that family. So why do they have different configuration? Okay, so let me talk on this. They actually acquire stable configuration. Okay, so Ce, how it will be represented, cerium 4 plus. Okay, so this acts as basically oxidizing agent. This acts as basically oxidizing agent because it's losing more electron, undergoing its self reduction process. Okay, so quite stable, we say the oxidation state, it gets acquire stable oxidation state. So this acts, cerium 4 plus act as an oxidizing agent. Whereas if you could see other elements like yttrium, right, and europium, all such elements, they will be acting as a strong oxidizing. Less number of electron will be lost by them. So europium and the yttrium, all these elements, right, they will go maximum for the 2, means less electron lost by them. So they undergo the oxidation process, and that acts as the reducing agent. So they are good reducing agent, strong reducing agent. Did you understand? They are a strong reducing agent. So from the oxidation state, we can have these two property. The first, we can say that it can be cerium will be acting as the strong oxidizing agent, whereas yttrium and the europium will act as the strong reducing agent. So there will be a question. Now let me put a question on this, because reasoning question, most of the reasoning question will come from this topic. So if I say, why is europium 2 more stable than cerium? Because cerium is more stable in which state? 4 plus 2 state, and then it will give the oxidizing reagent nature, right? So what is the reason behind it, why this is more stable in uh, um, +2 state, whereas cerium is not stable? So electronic configuration will help us to know. So this is the question. Okay, let me write the question first over here. Why is europium means, this is I'm talking to, europium 2 more stable than cerium? So cerium means I'm talking about this. Did you understand, Meda? Sorry,
Yes, ma'am.
did you understand?
Yes, ma'am.
Okay, so we can have this reason now. Electronic configuration. I will write the electronic configuration that will help you to know this. So electronic configuration of europium 2 plus, right? It will be xenon, okay? Xenon 4f7 and then 5d0 and 4s, because it has gone out, so that is also 0, so we'll not write. Okay, that is fine if we don't write, because this has gone out, electron has gone out. Okay, then if I write the electronic configuration of cerium 2 plus, so xenon, okay, 4f1 and 5d1. Okay, so this is the configuration. What you see in this case, 4F, if I draw for 4F7 for europium 2 plus. Okay, if I draw the orbital structure, look at over here. F has 7, 1, 2, 3, 4, 5, 6, and 7. So we can say all 7 orbitals are occupied, isn't it? 1, 2, 3, 4, 5, 6, 7. F has 7 orbitals. So maximum 14 electrons can be filled over there, right? What do you say this arrangement? It's half filled, isn't it? Whereas in cerium, what is the configuration? 2 plus, right? We say there is a 1 electron, 4f1. So that contains only one electron in one orbital. Rest all vacant. 1, 2, 3, 4, 5, 6, 7. Is this clear, Hridaya?
Yes, ma'am.
Huh. So what you find in this case, cerium, europium is more stable. Why it is more stable than cerium? Because it has 4f half field, right? It is half field, and half field gives more stability. Stable. It is quite stable, whereas this is unstable. Did you understand? Got your answer? Why is europium more stable than cerium? Right? Did you understand?
Yes, ma'am.
Okay. So configuration list I will send you today. Okay, I'll share with you. You can have a look and you can understand how electrons are getting distributed. As I explained you N plus L rule, that is how electron will be distributed. Okay. So that is not difficult part. You can take how the distribution half filled, completely filled being taught to you, and you can have a comparison. Okay. After electronic configuration, let us move on to the properties like size and other things. So when we are entering into the variation like among the lanthanoid and actinoid, so first lanthanoid, since we are doing the first point comes from topic size, is lanthanide contraction. What do you mean by lanthanide contraction? It's very most common question. Lanthanoid contraction and actinoid contraction, they ask, it is a most common question. Excuse me. So when we are talking about the size of atom in lanthanide group, we will be definitely seeing how this varies, right? Because it depends on the atomic size, right? Atomic radii. Since we are taken in ionic form, so we will consider over here ionic radii. So ionic radii may we will be having a concept that an atom, right, will be larger than the cation in the sense cation is smaller than their parent atom. Suppose X has formed, right, the after losing one electron, one X plus over here. This means this was having before, suppose for example, three shell, and the third shell was holding somewhere one electron. After losing this one electron, this shell get disappeared, right? You can see now. Now you can compare, this is the size of this compound, and now this is the size of this atom. So what we say, the concept, general concept we talk as, like, atoms are more in their cation, right? So this is the daughter atom and this is the parent atom. So what you find over here, X has the larger size than the X plus. Are you agree with me? Right. So what, how do we find here the variation? If we are talking about the lanthanide series, the ionic radii, when we are talking about the ionic radii, so ionic radii we find for the lanthanide, what is oxidation, maximum oxidation state shown by them, we can have that comparison, right? So we can find the ionic radii or atomic radii both, even atomic radii as well. Okay, both will have steady decrease. Are you understanding? They have steady decrease. Correct? So this decrease in the atomic radii, right, of lanthanoids with increase in atomic number. So that is why, because we can say the lanthanoid contraction, it happens. Okay, which has a unique nature. And why this unique nature is carried by lanthanoid? Because it has a poor shielding effect of F electrons. Did you understand? So what effect? Let me write the point over here. 3 major points I would write over here. The first is steady decrease in ionic radii as well as atomic radii. Correct? So first we found the size is decreasing. Correct? So this variation we are seeing as it is increasing its atomic number. Correct? Are you clear, Hridaya?
Yes, ma'am.
With increase in atomic number, as we move to higher atomic number atom, that will have a decrease in their atomic radii. Why is that so? There is contraction works, lanthanoid contraction, which is called as, due to which it is showing decrease. And this is a unique property. It's a unique property, does not have with other element, unique property. Okay, so why this contraction occurs? What is the basic reason behind the contraction? So let me tell you, this is due to the poor shielding effect of electron, right? Due to poor shielding. Poor shielding, are you understanding? Shielding means, did you understand the meaning of shielding? Let me tell you, explain this shielding effect. Shield means, right? We are protected by our parents. So that is our shield. Tell me.
Yes, ma'am.
Yeah. So we see this is atom, correct? Nucleus, and we say they are orbit, they revolve around them. So what happens basically in this structure? The previous orbital will always act as a shield for the outermost orbital, right? So maximum, this is called the K shell, this is called the L shell, correct? So K shell can have maximum 2, L shell can have maximum 8, then 18, but should not have more than 8 in the outermost shell. Correct. So always this previous shell is acting as the shield. Shield in the sense it does, like it protects this electron from the nucleus. Like, because there is an attraction. This is negatively charged, this is positively charged. So obviously the invisible attraction which is not visible to us, it will be working between them. Okay. So this previous shell of this, because electron cloud is more, it does not let this effect to be work more on the outermost shell. This effect we call as the shielding effect. So as the atomic number increases, shielding effect increases. Did you understand? But what happens over here? This 4F is anti-penultimate shell. Anti-penultimate means before 1 or 2, it falls into the shell. So that is why it is called the anti-penultimate shell. So even before it falls, how this shield will work? Shield will not work, right? Because it is falling before the orbital. So orbital, because sixth is the period, means 6 shells are there total. 1, 2, 3, 4, 5, 6, but this is falling into the 4f. Fourth n value is equal to 6, but it is falling into n minus 2f. Did you understand? That's the reason shielding effect is not working over here. Did you understand, Hridaya? Due to poor shielding effect of F electron. That's the reason for lanthanoid contraction. What is lanthanoid contraction? Steady decrease in ionic radii and atomic radii among the lanthanoid series with increase in atomic number. It's easy, right?
Yes, ma'am.
Good. So this is most important point we have in our chapter, this, right? So now the next most important, the consequences they ask for the 2 marks question. Write the consequences of the lanthanoid contraction. Okay, consequences. Okay, so let me tell you covalent character of cations here it is increases. Okay, electronegativity of trivalent ions increases slightly. Basicity decreases from lanthanide to lutetium. These are the 14 elements. And the E naught. E naught is the means standard electrode potential value also increases. So what are the things increases? I would just write what are the properties we are finding increasing. Okay, and what is decreasing, and then it will be very clear to us, need not to go in a point. Okay, the most important consequence I will say that due to the lanthanoid contraction, the atomic radii of zirconium, ZR means zirconium, it will be possessing 160 picometer of the atomic radii, and hafnium, HF means hafnium, it will possess 159 picometer. This is almost the same, only one digit difference is there. Correct? Did you understand?
Yes, ma'am.
So they will occur together. This is the one consequence we will see. Okay, so therefore, or hence we can say it is difficult to separate them, right? This is the most important consequence we will see. So this I had discussed, and then what did I say? I will write increases, and then I will say what are the properties increases. So let me tell you what are the property covalent character. So it will be easy to you, and then once you are prepared the mind map in your right concept mind map, then you can explain in your words. So covalent character of cations increases. Clear? Second property, what I say? Electronegativity of trivalent ions. Electronegativity of trivalent cation. Those who are having oxidation state +3, their electronegativity, I meant to say. Then E naught. What do you mean by E naught? It is a standard. Wherever naught is put now, that is a standard. Standard electrode potential. This also increases. So easy to remember, right? Covalent character of cations increases, electronegativity of trivalent cation increases, and standard electrode potential. These all values or the terms are increasing. Then what this decreases? The one characteristic which we have seen decreasing is that basicity. So basicity decreases. That decreases from lanthanum to lutetium. It's easy, right?
Yes, ma'am.
Okay, now let's see some general characteristics. How do they look, and how we can have a compound? This is compound called lanthanide compound. So some characteristic they may carry, okay, they may have, or they may associated with some properties that helps us to know that is the lanthanoid. So let's see that lanthanides. What are the lanthanides characteristics we have? First thing, how do they look like? They are silvery. They are silvery white metals. Okay, so shiny appearance they carry. Okay, but they get tarnish as metal has a reaction, no? Tarnish in air. So tarnish in air means one layer deposition of the oxide we can have. We can see this is possible. Okay. Second property, what you can see, hardness. They are hard, and this hardness behavior increases with the increase in atomic number. Okay, they since we have seen they are metal, right, and they are hard, the next property is conductivity. They are good conductor. They show conductivity. Just a minute, baby, not here. Mama is taking class. So conductivity shown by them. Okay, this is the most important property. They are conductivity towards to heat and the electricity, both they have. Clear? It is clear?
Yes, ma'am.
Okay. So here I would say the some ions like all lanthanides ions except uh, all lanthanides ion. Okay. So except we are having few like example, I would say La3 plus and Lu3 plus. Except these, all are colored. Let me. Somebody is there near the yeah, so it is clear, right? So all lanthanides will have the color compound behavior. We have exception. I have highlighted over here La3 plus and Lu2 plus. They will not have the color compound nature. Okay, these ions they do not go in a colored form, right? It is clear.
Yes, ma'am.
So they will be colorful in nature. Just a minute. So here we can say lanthanoids even have other properties associated like magnetic behavior. So let me tell you like almost all ytterbium and lutetium 3 plus, those are the compounds. Except those others are paramagnetic. Even they show the paramagnetic behavior as well. And you know what is paramagnetic? Paramagnetic shown because they are having presence of unpaired electrons. Yes. So this is the most important now. Chemical properties, how to be studied of this lanthanoids and actinoids. So we say the lanthanoids are having a reaction with oxygen. As you have seen, the tarnishing is possible. It even reacts with the carbon, right? It forms the lanthanide carbon compound. So we are basically seeing almost most of the characteristics seen or reactions seen by the metal as the metal shows. So I would be writing in a flow chart that will help you a lot. So lanthanoid, I am representing by the symbol Ln. As I said, the together group can be represented by lanthanoid. There are two spelling I am writing. Can you see? One I wrote with the lanthanide and another I have written with the lanthanoid. Did you understand? So when I'm writing lanthanide, look at over here. Did you understand? Meda, sorry. Yesterday, Meda class was very much. So Meda is coming in the. Okay, are you understanding? So lanthanoid, when we are talking, I meant to say the Ln. It means the whole family. It is represented with the symbol Ln and the called as lanthanide. Are you clear?
Yes, ma'am.
So I will have a symbol for all group representing Ln. Okay. This is whole group representing. Okay. So let us now Ln reacting with first reagent what we have. It can react with the oxygen. It can react with the carbon. So when what happens when it reacts with the oxygen? It reacts with the oxidation state +3. Remember, they have the most common oxidation state +3. So when it reacts with the +3, oxygen is -2 and lanthanide is +3. Okay, lanthanide. So I would write like this, 3 plus 2 minus. After exchange of their ion, Ln take the oxygen and oxygen takes the Ln oxidation state. We can have Ln2O3. So what does Product formula carried by this Ln2O3. Did you understand? Now, after balancing, we'll have different number of moles over here. That is not a very difficult part. Okay. Now, since we are taken common, let us move on to this and separate when we write, when then we can do the balancing. What happens when lanthanide? Let me write the spelling also. Lanthanides, right? So when they are treated with the carbon, what happens? Then lanthanoids will be combining with the carbon, correct? And what do they produce? Carbide. Okay, what do you call that? Carbide. So we are taking Ln3 and C. Did you understand? So they form basically carbide. This is the formula. Then reaction with we have with this carbon, other possibility also there where we can have lanthanide plus 2 series, right? Plus 1, plus 2, plus 4. The such series are also possible. So we can have like carbide compound in a different composition, right? So let me tell here itself, I would say possibility goes, increase the line, I'm increasing, so it can form even Ln2C3, even it can form LnC2. All these are possible. Okay. The next reaction with the dilute acid, if I take acid, suppose hydrochloric acid, or suppose we am taking sulfuric acid, so it will be as metallic nature, metal displaces hydrogen from the acid, same way a hydrogen will be displaced from this acid. So what we get as the product? Hydrogen gas. Did you understand?
Yes, ma'am.
And now what happens when it is treated with the halide? Halide means X is equal to, tell me, Br, Cl, all I'm talking to. So what does it form? Lnx3 as the product. Okay. This is the product produced over here. Now, what happens when it is treated with the water? It gives the hydroxide. So alanine plus 3 state. So it gives the hydroxide precipitate and gives out the hydrogen gas. General reaction we are writing. What happens when it is treated with the nitrogen gas? It forms the Ln nitride. Okay. What happens when it is treated with sulfur? Right. So it is formed the Ln sulfide. Okay, so these all formula coming out from their valency. Like we know the X is -1, OH is -1, Ln is -3. So 3, 3 get cancelled, and S is -2. Are you able to understand? So one formula I taught you, for example, 3 plus है, and it is -1. After crisscross method, Ln takes this number as the subscript down, and this number goes to X. So the formula comes as Ln X3. Did you understand? Similarly, LNOH, these all extra information. Ln3 plus and OH minus. So what will be the crisscross way? We can have Ln gets the one number over here and OH gets the Ln ka oxidation as the number. So we get LNOH whole thrice. Similarly, Ln3 plus and nitride 3 minus oxidation state. Their valency I meant to say. Ln3, all right, N3. So both the 3 3 divisible number get cancelled. What we get number, formula as Ln N. Similarly, we have Ln and sulfide 3 plus and 2 minus. So crisscross, what do you get? Ln2 and S3. Did you understand? 2 and 3 it's not divisible, different number. One is odd and even number, right? So we cannot divide it. Did you understand?
Yes, ma'am.
Okay. So now we are completed with the lanthanoids. Now we are having the actinoids. There is a one question, that is the one short note, one time, one mark question sometimes comes over here. Composition of mixed metal, right? What do you mean by the mixed metal? Okay, so they ask the composition basically. What composition belongs to this, or what is the composition basically present in it? So lanthanoids will be taken in a maximum quantity. Lanthanoids, where the quantity go almost 95%. Okay, plus we will have iron, which is not very much, approx we can say goes to 5%, very less. And then we can have rest all. like not approx it is taken, no? So other like 0.000 some that is called traces form, right? So traces of, we can say, impurities like carbon, sulfur, calcium, okay, and aluminium, all these traces will be present in this. So this is whole composition, mixed metal. Now where do we use this mixed metal? Actually is used in alloy formation, like magnesium. If we wanted to combine with this metal, then we form the alloy like bullets shell, light, we can say lighter flint, all those things will be made from this compound. Okay, so this is called the mixed metal. Did you understand?
Yes.
Uses, I will tell where we use this in making magnesium alloy. Okay, so this will produce, right, bullets, shell, and lighter flint. Okay, this is the uses of this magnesium alloy, and this compound mixed metal is used in the magnesium alloy formation. So overall lanthanides we have completed. So what are the important topic we are having over here? We have discussed about it. Come to the actinoids. Next topic. Actinoids, we can say this, we have elements again here from 14. Total, how many elements do we have? 14 elements. So this also carries 14. From where to where, if I wanted to tell, thorium to, right, which has the atomic number 90, okay, and lawrencium. Don't do that, Raghu. So lawrencium, let me write the spelling. LW is the symbol, but let me write the spelling. It will be helpful. Lawrencium. So atomic number 103. Till here we call the actinoid. So total 14 elements are there. Now what is the general electronic configuration for this series? They are called 5F series, right? We have found that also how to get the 5F series. So what is the general electronic configuration for this? Radon is the noble gas before this group present. So we'll write that 5F, okay, 1 to 14 electrons, and then 6D, 0 to 1, and 7S2. This is the general electronic configuration followed from thorium to lawrencium. Okay, now again the same topic comes over here. What do you mean by actinoid contraction? Actinoid contraction. So let me tell you again, steady decrease in size, atomic size of the actinoid, right, across the actinoid series is called the actinoid contraction. Same definition, instead of lanthanide, what we will keep? Actinoid. Are you clear? Hridaya, you can write,
Yes.
follow as usual. But instead of lanthanide, what you are writing over here? Actinoid. Okay. Oxidation state. The most common oxidation state is also here same. +3 is the most common oxidation state. Okay. What are the other oxidation states we have for the elements of this group? We can have +4, +5 other oxidation states, but this is most common. Okay, +4, +5, +6, and +7. These are the other oxidation state possible here. Okay, now sometimes say they ask, name the element which will be having +7 oxidation state. So let me tell you, Np, neptunium, and the plutonium. So these two elements, they have the +7 oxidation state. Clear? General characteristic, how do we identify, right? Seeing the nature. So general characteristics may these metals are also silvery metals. Okay, these metals, the most important point in this is radioactive. All uh, these actinoid series having the radioactivity. So they are highly reactive. Even in their finally divided form, if they are present, they are highly reactive. Since they are radioactive, you can imagine. So all actinoids are radioactive. The most important silvery metal, they are, and they are radioactive elements. All the elements of the actinoids radioactive. Correct? Highly reactive. In which form? When they are present finally divided form, powdered form. Right? They are also having paramagnetic nature as like a lanthanoid. They are also having paramagnetic behavior because unpaired electron present over here. Okay. They are also reacting towards to the oxide layer because oxygen ke saath it is very much reactive. Okay. Now let me tell here, Hridaya, we have difference between lanthanoids and actinoids. So two differences you can remember. Difference between lanthanoids and actinoids. So when we do the difference, not more, but yeah, two differences we can remember. Lanthanoids and actinoids. Here what we can say, electron enters into 4f, and here electrons enter into 5f. This is the most important difference. So this is called the 4f series and this is called the 5f series. Yes, Hridaya? Correct? These elements, they are non-radioactive. They are not radioactive. But here actinoids, all are radioactive. Correct? You have read just now. So this can be given as a major difference. Very important. Correct? Basicity we are finding here decreases. So they are less basic. Correct. Here they are more basic. Single word will be remembering for longer time. Okay. Here the oxidation state, maximum oxidation I am telling, not the common oxidation state. I am talking about the maximum oxidation state. So maximum oxidation state shown by the element over here, it is +4. Okay, but here it is shown by it's a +7. You have seen, right? So here it is shown by +7. Okay, and they have greater shielding effect than the 4F. 4F has very poor shielding effect, very poor. Lanthanide contraction is lesser. Okay, so let me write over here first to lanthanide contraction. If we compare, lanthanide contraction is lesser, not much as compared to actinoid. So why it is less? So the reason is 4F electrons have greater shielding effect. So reason also you got, sometimes they may ask you reasoning question. So it is important. Let me just mark. Okay. Now here what we are seeing, actinoids contraction is greater. Why it is greater? Due to very poor shielding. If 5F electrons have poor shielding, right? It is clear?
Yes, ma'am.
Okay. So we have finished the actinoids and lanthanoids, the possible questions and chemical properties which we have in our syllabus. I have discussed with you. So do remember this. We have completed the chapter D block elements and the F block elements. Now I would like to start the P block elements. Can we go for that? P block elements. Vidya? Okay, so the P block elements it is actually a huge chapter, but we will be trying to finish in a systematic manner, like what we have to study from this chapter, how can we have a good mark from this, and because your last, let me tell you, it's a very important and scoring chapter as well. Okay, so I am taking you to all the most important part of the we have syllabus. May what is this? So let me tell you, this chapter holds 10 marks. P block elements. Okay, so total 10 marks expected from this chapter. So we can expect the part A may one question. Okay, this can have one question. Part 3 may we can have one question. That is A, C, correct. And then we can expect the question, yeah, part C may we can have 3 questions. Like total 3 questions can come. So three, yeah. So it is 1 mark and 9 total. So total is 10, right? Like this we can expect. Now here, what are the group you have to study? Let me tell you. In the previous class, you might have studied the P block elements basically starts from group 13 to group 18. These two together, what do you call as the P block elements? Isn't it, Rudya?
Yes.
Huh. So total, how many? See, group 13, group 14, you have already studied. So that's not, again, you need not to study. We have this P block called P block because their electrons enters into the P block, last electron. So they are called as a P block elements. The name of the element P block, S block, from where did we get? From the entering electrons into the valence shell, last shell. Correct now, since enters last shell, last electron, valence electron into their respective block, that's reason we are calling them as the P block, like that. Okay, so now let me tell, here we need to study group 15, 16, 17 and 18. All these groups we need to study. Okay, so the elements over here, nitrogen, phosphorus, in the group 15 we have that all. So everything we have, and as the, let me tell you, as the most important chapter, I would tell this is very important chapter and very easy also. Very easy, like most of the things we need to remember. Understanding is there, but more preparation needed over here. Like you need to read a lot in this, that's all. Okay, the formulas and all those things we need to remember. So now let's begin with the first group, group 15 from this family, P block elements family. Group 15 has the elements, let me write, nitrogen, phosphorus, arsenic, antimony, and then bismuth. These are the element. So what did I say? It's a nitrogen, it's a phosphorus, it's a arsenic, right? Then it is antimony. So what is antimony? Ant, antimony. And then we are having bismuth. Symbol goes N, P, As, Sp, and Bi. Okay. So these elements we call as the nitrogen family. What do you call this as? Nitrogen family together. Okay. Now, generally, this is called the pinkogen. Group 15 is called general by the name pinkogens. Okay, it is called the pinkogens. It is actually basically we say most of the elements are mineral forming, salt formation they are having, right? So we are calling them as the pinkogens by the name, common name. Okay, now here most abundant gas. Nitrogen is 78% by volume in the air, it is present. Correct. So here the nitrogen is the most important we will consider, and the property, reaction, its structure, and I would say the compounds of the nitrogen we had in detail. Okay, so study. So first we will learn the general property. From that, after that we will pick one element and study in a detail about it. Okay. So general properties, I would discuss first general electronic configuration. What is the configuration? General electronic configuration. Always is first property start with the general electronic configuration. So the configuration for this group, specifically group 15, noble gas, previous noble gas, and NS2NP3. This is the general followed from the nitrogen till bismuth. Okay. So here we say nitrogen to bismuth, they are following the NS2NP3. If you wanted to write the electronic configuration, you can check. A nitrogen is 7. So noble gas before it is present is the helium. Correct. Helium, 2 electrons represented, 5 electron, how it will be represented? 2s2 and 2p3. This is the electronic configuration. Like this, phosphorus 15. So phosphorus, before phosphorus we have neon. So 3s2 and 3p3. This is the electronic configuration. Did you understand? So on. Did you understand, Hridaya? Like this, we will go for arsenic, we'll go for antimony, and we'll go for bismuth. So then general, what you will see at the last electronic configuration, the period of that, and the block where we have written S2 and P, their electrons will enter. Right? Now, this is the electronic configuration. Now, let us talk on the atomic size. So, we say the covalent and the ionic radii will be having change in this, that is increases down the group from top to bottom, means from nitrogen to bismuth. Okay. So, let me write the properties over here, physical properties and their variation. The first is the covalent and ionic radii. Correct. What did I say? It increases as it moves down in a group from nitrogen to bismuth. This is increasing as it is going down in a group. Okay. So we say why it is increasing. What is the reason behind it? So let us know this also. Right. So we can say the completely filled D and F orbitals as we are going down, right? That becomes heavier. For heavier members, that becomes more. So as the D block and the F block, we can say present over there due to the presence of completely filled D. 6, 5, 4, 5, they will have the completely filled D. Even 6 and 7, what they will have? F orbital included in this. Okay, so let us include F orbitals also. So as we are going down nitrogen to bismuth, we can see these elements will have their D and F orbitals completely filled, due to which they show the increase in ionic and the covalent radii. Okay. This is the first property. Second property, what we say, the ionization enthalpy. What happens to ionization enthalpy? Ionization enthalpy decreases or increases. So let me tell you, an enthalpy general, what we learned, that decrease down in a group. The same variation we can also find over here. There is decrease in the IE when it moves down in a group from nitrogen to phosphorus. Decreases in group. This is from nitrogen to bismuth. Okay. This is about the ionization enthalpy. So why ionization enthalpies of the group 15 decreases down the group? Because they are again the same reason we can say smaller, the size it increases. First thing, the size increases and it gets more stability and easy to release electron from that. So that is the reason, because the generally we have learned that why enthalpy increases down, sorry, increases across the period, because there will be common the number of shell, but increase in nuclear charge. And here in a group there will be a increase in number of shell, nuclear charge also increases, but that gets dominated, right? Size works a lot over here, right? So can we have some few minutes break and then we connect? May Hridaya? Ionization enthalpies, two factors are important. First is the atomic size. As the size increases down in a group, so as ionization enthalpy decreases. And second is the nuclear effective charge. So this nuclear effective charge increases, but it is getting dominated by the atomic size. Okay, so that does not work a lot. So what we see as we go down a group, atomic size increases. So due to increase in size, we can say the last shell will have less attraction towards to the nucleus, right? And it will become little free, less we can say loosely bounded electron in the valence shell, phase late can be removed. So it requires less energy. So energy decreases as we go down in a group. It is clear?
Yes.
Okay. The next, after ionization enthalpies, we are going to learn about the electronegativity. Electronegativity also decreases. This also depends on the same two factors. From nitrogen to bismuth. Metallic character. Metallic character, it is increase, it is shown because increase in atomic size, both are directly proportional. So as the atomic size increases, we can see atomic due to increase in atomic size, metallic character increases. Both are we can say directly proportional to each other over here. Okay, let me tell you the element ka specific characteristic. Nitrogen is a non-metal, correct? It's a gaseous form, so this is non-metal. Phosphorus is also non-metal, right? Arsenic, antimony, these are metalloids. Metalloids, what do you mean by metalloids? Having the both characteristics or the intermediate between metal and non-metals. And last, bismuth is a metal. Got it?
Yes.
Did you understand?
Yes, ma'am.
So it is very important. That's why I highlighted and showed. Now, oxidation state. What is the oxidation, common oxidation or general electronic oxidation state we have? Common, let me talk first. Oxidation state +3, -3 as well, and +5. So with these, you will see the compound, right? So exhibit -3, this will be decrease. -3 oxidation state decreases as they go down because metallic character increases there, correct? So this decreases down in a group. Why? Due to increase in metallic nature. It is clear, Hridaya? It is clear, right? So we can say bismuth, which is in a 5 oxidation state, +5. It will be oxidizing agent, right? So strong, it will be strong oxidizing agent. Clear? There is a question, nitrogen, why it is restricted to a maximum covalency of 4? So when we are seeing its valency, valence electron available 1, 2, 3, 4, 5. But nitrogen has restricted its maximum. Why? Because it only 4 orbital. Correct. Its atomic number is 7. It has 1s2, 2s2, and 2p3. Correct. So it has only 4 orbitals. What are the 4 orbitals? S and p. Correct. So at this level we will not consider. First level will not consider. The second level, which are having the very less energy gap, 2s and 2p, that is considered together. So second level pe what you will see, there are total how many? S orbital single, p orbital, that is 3. So total how many orbitals are there? Total 4 orbitals are participated. The px, py, and pz. This is s orbital. So since in nitrogen only 4 orbitals are available for bonding, so it will not go beyond 4. It will always restrict it covalency. So question I will put over here, very important question, and this is the reason I'm going to give. Nitrogen, don't Raghu, why? Wow. Nitrogen is restricted to a maximum covalency of 4. Why? This is the question. Hridaya, are you able to understand? So why? What is the reason? What we are going to write the answer, Hridaya? I explain you this on this base of this. We can say because only 4 orbitals, that is 1s and 3p, correct, are available for bonding. I hope I'm clear to you, Hridaya.
Yes, ma'am.
Are you able to understand why it is restricting beyond 4 or more than 4? Because it is not having capability. So if you have more than 4, it cannot go because it has only 4 orbitals, right? Now that is the reason it will have the anomalous property, and that's the reason we are specifically learning about the nitrogen over here. Okay. So all those properties we have questions. So I have, yeah, as I said, the model papers and the question paper, all those I have stuff. Based on that, I am teaching you what is the most important and the we can say the frequently asked question that highlighted. I am teaching everything. I am teaching. I'm not leaving one small topic also, right? And highlighting simultaneously, I'm highlighting the most important topic which is important your examination point of view. Now come to anomalous behavior. What do you mean by anomalous behavior? The behavior which is different from others, or which some characteristics which makes the um, element differ or different, behave differently, right, from other elements. That is called the anomalous behavior. So we have over here with the nitrogen. And why will be this characteristic found in this? Because some reasons we have. Okay. So what is the reason? Anomalous behavior of nitrogen we are going to learn. Why nitrogen is specifically showing different characteristic? Because the first and most important is small size. It has a small size, very small in size. First element is small size. Second, as the electronegativity decreases, so this has high electronegativity as compared to other element, right? So it will have more capability of attracting electron towards itself, correct? Then it will have high ionization enthalpy as well, high IE. Other elements having decrease in that, because down in a group it decreases. Then most important, we can say not having d orbital. It does not have vacant d orbitals for the bond formation. That's why it cannot extend its valency more than 4, right? So we can say that is the reason we can find it cannot form a compound more than 4 covalency, correct? And capacity it will be having to form only p pi and p pi bond, not more than it. Okay, clear me, Hridaya? So these are the character reasons with because of these reasons nitrogen has the anomalous characteristic, anomalous property. Now what are the anomalous property we are seeing? Like we can say nitrogen is a gas, but other elements they will be in a we can say a metal form, solid, like phosphorus, arsenic, antimony, and bismuth. So let us see the anomalous characteristics of nitrogen. So nitrogen is a gas, but other element are solids. I meant to say phosphorus, arsenic, antimony, and bismuth. These all elements are solid. Okay. Second property, nitrogen is diatomic. Okay. Where or while other elements polyatomic, right? So phosphorus example, we can take P4 exist in, right? Next, nitrogen can form multiple bonds like P pi itself, whereas other can form P pi d pi. It does not have d orbital. So this bond is due to large size. D orbital is available, right? And availability of d orbitals, right? So most important anomalous characteristic, let me highlight this part. I would say that nitrogen has p pi p pi. This is very important reasoning question. Why nitrogen can form only p pi bond with itself, multiple bond may, whereas other elements of the group will be able to form p pi d pi bonds. Sorry, Hridaya, today my son is not keeping well, so he is not gone to school. He was disturbing in between the class. So it's okay, you play over there. Mama is teaching. Go take the car and go sit over there. So this is most important. Why we will be or will be finding this characteristic in this nitrogen. That is most important, smaller in size and unavailability of the d orbital. Whereas other elements, phosphorus, silica, bismuth, they are all large in size and they have availability of d orbital. Since they have these characteristics, they go for p pi and d pi bonding. Are you able to understand? Hridaya? So this is the most important anomalous characteristics of the nitrogen. Hridaya, it is clear to you?
Yes, ma'am.
Okay. Now, can we go for reactivity? Reactivity of the elements in towards other elements or compound, like reaction towards hydrogen, oxygen, halogen. Okay, we'll learn in general. So group 15 elements.
Elements क्या
Hmm.
मतलब से क्या है
Animal अलग होता है. This is element.
elements
It is not animals. Element. ಆಯ್ತು ಮಾ ಸರಿ say bye to auntie. So group 15 elements reactivity towards, first we are going to learn about the oxygen, hydrogen, and then halogens. So let's start with the air or hydrogen. Let's start, no problem. Baby, please sit. Sorry. Stand over here. Let me teach. Otherwise, Mama will go to that computer. Please. Good boy. Okay. Yeah. So hydrogen's a reaction. First, we will learn what happens when this group 15 reacts with the hydrogen. So reactivity, please remember that what is the oxidation state of nitrogen family. We are learning in general. So we can say this will be showing the +3 oxidation state, right? +5 oxidation state, -3 oxidation state, but which is common oxidation state and most found, like common with the all elements, there is no decrease. So +3 is the mostly found oxidation state in this group. We will be taking this oxidation state in general and talking. So let's see. So it means the oxidation state of element over here is 3 plus. Correct? What is the E for? E for group 15 elements, I meant to say. Did you understand? And hydrogen oxidation state is here taken in a non-metal form, hydride ion. So in general, I can say it forms a compound called EH3. Right? It means they form trihydrides. Right? So if I'm talking about the nitrogen forms NH3, phosphorus PH3, arsenic ASH3, correct? And this antimony H3, bismuth BiH3. So this is how hydrides will be formed. Now variation, how it varies, correct? So variation, we can say it goes decrease or increases depends on the bond dissociation energy. Correct. So when we are talking about the stability, which is more stable among ammonia and the bismuth, we say ammonia is highly stable. Why it is highly stable? So stability of hydrides, it will be decreasing down in a group. Stability decreases. Why it is decreases? Why stability decreases? What is the reason for this decrease in the stability? Because we find mat karo please. Due to the decrease in bond dissociation energy. Okay, so ammonia, if I'm asking a question, for example, uh, in group 15, ammonia is quite stable or it's highly stable. Why? What is the reason? So we say as the stability decreases down, right? So NH3 being the first compound will be highly stable. And why? Because the bond dissociation energy, it's very, we can say, high for this molecule as or compound as compared to the other compounds. So now this can be leading to other property, reducing behavior. In opposite can be studied. So what will be the reducing behavior? If you are seeing the characteristic dissociation is getting down, it decrease. So we can go for the opposite direction. This is how, like if I go from top to bottom, right? top to bottom, then this will this characteristic, reducing characteristic, increases top to bottom. So when I'm talking about the reducing behavior, what did I say? These in these compounds, bismuth has high reducing characteristic.
Ah, mommy.
As compared to ammonia, right? So why the reducing characteristic is increasing as we are going down? So this actually we say the again bond dissociation energy. As the dissociation energy decreases, so we get dissociated easily, and that can act easily available for the process, right? Reduction process acting as a reducing agent. Correct? So that's the reason we can say as we go down in a group, reducing characteristic increases. So bismuth will be holding highly reducing power as compared to ammonia. Now let's talk on basicity as well. Ammonia, pH 3 and ASH 3, antimony H3 and bismuth H3. If I talk about the basicity decreases down the group. So ammonia is highly basic. We know ammonia, it's a basic characteristic it holds. So ammonia is highly basic. Got it? Second property, reactivity towards oxygen. Right? So when we are talking towards oxygen, remember it can react with the +3, +5 oxidation state. So when it goes, sorry, when it goes, maybe you are coming to tab, please. +3 oxidation state. Okay, so these are the elements oxidation state. Oxygen oxidation state is 2 minus. So what will be the oxide oxidation? E2O3. And if it is +5, E2O5. Right? So it reacts with the two elements oxidation state +3 and +5. Oxide will be -2. So when it is +3, it gives E2O3. When it is +5, it gives E2O5. Are you clear? So basically, we call it as a trioxide, and this we call it as a pentaoxide. 5 for pentaoxide. So we get when it reacts with the oxygen with the +3 trioxide with the +5 pentaoxide. Okay. Now in this characteristic, we have a very important topic, which is amphoteric, acidic, all basic. That characteristics we have to check now in this. So when we are taking example of nitrogen oxide, for example N2O3 and P2O3, so it means I'm taking the nitrogen +3 oxidation state and phosphorus also in +3 oxidation state. Correct? So we say these two being non-metals, they will be acidic oxide in nature. Their oxides will be acidic oxide. Are you clear? Why? Because they are non-metallic oxides. And we know the non-metallic oxides are acidic oxides. Clear? Then when we are going for the down, extremely down. Okay, so this characteristic can be understood in this way. Very easy. Nitrogen, phosphorus, arsenic, antimony, bismuth. So these two are non-metals. These two are metalloids, and this is metal. So since it is non-metal, will be acidic oxide nature. Metalloids, amphoteric means both the characteristic. Amphoteric metals means basic oxide. Did you understand? This is how can like we can relate, and we can make a chart and we can study. So P2O3, and then arsenic also we can write As2O3. Antimony also we can write as B2O3. These two are amphoteric. Why amphoteric? Because they are metalloids, amphoteric oxides. So name an amphoteric oxide from group 15 elements. So arsenic oxide or antimony oxide. So if you remember their metalloid behavior, metal non-metal behavior or metal, you could be able to differentiate them as acidic, basic and amphoteric. Right? So there. Last is bismuth oxide, B2O, BiO2, O3. So why it is an basic oxide? Because it's a metal. So metals, they provide basic oxides. So you can make this chart, you can study, because that's the reason I have told you the first itself. This is very important besides a lot characteristic over here. So I'll differentiate metallic and then do remember these three. Okay. So this is basic oxide because metallic, amphoteric because they are non-metals, and acidic because they are non-metal. Sorry, they have metals and non-metal. Amphoteric. Okay, very important question. 1 mark question. Let me mark here. It's a very important topic. Now let us move on to next. The third, reactivity towards halogens. How do they react with the halogens? So the same, +3 oxidation state and +5 oxidation state. So if element is possessing +3 or element is possessing +5 oxidation state, we know the halides will be X minus. So with this, they will produce EX3. And with this, they will produce EX5. Okay. So this all depends on the in the oxidation state the compound comes and okay. So pentahalides, they say why the question comes over here, reasoning question. Let me put over here for you. Pentahalides. Pentahalides means EX5 I'm talking to. Pentahalides are more covalent, right, than trihalides. Why? This question is very important. So let us learn why. Okay, so pentahalides are more as covalent than trihalides. What would be the reason if we are seeing comparing? So in case of nitrogen, there is no pentahalides because does not have the availability of d orbital, but trihalides is possible. That is quite stable over here. Correct. So other elements we can say like phosphorus and what we can say bismuth, antimony, and arsenic, all they are having d orbital. So they are stable in which orbital form? D orbital. They have maximum capability of forming compound with the d orbital. But nitrogen is only stable in the trihalide, not in the pentahalide form. Okay. So why it has the nitrogen exhibit does not form the pentahalide? So reason we can give the same. And why pentahalides is more stable? Because due to d orbitals or availability of d orbitals. Okay, maximum covalency it can go in d orbital way, but nitrogen case this is not possible. So the other question can be framed over here. Uh, why nitrogen is stable in trivalent and does not form pentavalent? Or why nitrogen forms only trivalent, not trihalides, not pentahalides? Okay, this question can be raised. So here what will be the answer? Hridaya? What is the answer, Hridaya? Because d orbital is not available, na? So it will not go for the +5 oxidation state. It is clear?
Yes.
Nitrogen has only p orbitals. You have seen, right? In explanation, covalency explanation, same will be repeated over here. So in a sentence I am writing, it does not have d orbitals to expand its covalency beyond 4. Same reason I have written in sentence. So it does not form pentahalide. Hridaya, it is clear to you?
Yes, ma'am.
Okay. So this is about the reactivity. Even they can ask a question, Hridaya. PCl5, other question. PCl5 means phosphorus pentachloride is known, means it is present, but not NCl5, means nitrogen pentachloride. Why? So you can answer, right? Because Hridaya, you will be able to answer because phosphorus contains d orbitals, right? Whereas nitrogen does not contain d orbitals. Clear? It is clear, Hridaya?
Yes.
Now let us learn the nitrogen compounds. First, we will pick dinitrogen. In this preparation, properties, everything we need to see. So how dinitrogen is prepared? Ammonium chloride के साथ reaction. It's a laboratory method. Ammonium chloride treated with sodium nitrite NaNO2, and this gives out NaCl, okay, plus water and plus liberates dinitrogen gas. This is how dinitrogen is prepared. Okay, it is clear. Second way, this is the first way. Second way, even we can have ammonium chromate, dichromate. Okay, so ammonium dichromate NH4 whole twice Cr2O7. It is dichromate. When we heat this compound, decomposes into chromic acid, Cr2 chromic oxide. It is called as water and nitrogen, dinitrogen gas. Clear? Here needed 4H2. That's all. Second way. Next way I meant to say, even it can be obtained from sodium and barium azide. What is barium azide? BaN3 whole twice. This is nitrogen azide. Barium azide. Nitrogen ko we call it as a azo also. So azide it is. So when we take this compound, thermal decomposition, heat needed just That's it. It gives the barium compound and nitrogen gas, dinitrogen. So let us balance three nitrogen needed over here. Second, even sodium azide. Sodium azide ka formula is NaN3. I'll teach you how to get the formula. Don't worry. So we get the sodium over here and nitrogen over here, gas. Okay. To balancing the equation, what we do over here, nitrogen gas 3 moles, right? And sodium, total 6 now. So here we will 2 and here we will have 2. It is balanced, right? So these all are actually barium is 2 plus, nitride is 3 minus. So what will be the formula? BaN3, it is, right? Because nitride they have said, so O comes as 2. So N3, N triple bond they are. And then it is reacting with the barium 2 plus. So we say this is BnN3 nitride form, which gives a compound. Got it? Sodium nitride, only one sodium ion and nitride 3 minus. So it is Na goes in a N3. Here the crisscross will not because 3 nitrogen atoms are taken. Nitride ke liye. That's the reason. Okay. This is how dinitrogen is prepared. So what do you mean by the dinitrogen? Dinitrogen is like we say N, each two nitrogen atoms combine and they share their electron, 3 electrons, and we bond triple covalent bond and 2 lone pair left. This is lone pair. Correct. So why did we form the dinitrogen structure like this? Look at over here. How do we decide? Nitrogen 2 and 5. So there are 5 electrons. These 5 electrons can be done octet completion after adding 3 more. So since needed 3 more electrons to complete the octet, so they keep their 3 electrons in front of each and share then the complete octet. Did you understand? Hridaya? Hridaya, did you understand
Yes, ma'am.
about the structure? Okay, come to properties. So we don't have much properties for dinitrogen, very less. Nitrogen ke saath reaction and we have with the oxygen. This is basically as the anomalous characteristics also seen, the same characteristic in the diagonal relationship also can be formed. Like nitrogen is the one element which can has a relation between the lithium and the magnesium and they are diagonally related, lithium and magnesium, because they have a reaction towards nitrogen. So nitrogen reacts with the metal and dinitrogen specifically. I'm saying what are the metals reactivity? Specifically lithium and magnesium. So dinitrogen reacts with lithium and magnesium. So when it reacts with the lithium, it gives lithium nitride. Okay. And when it reacts with the magnesium, it gives magnesium nitride. So here the formula crisscross will apply because we are not using the triple bond and triple bond 3 times. So will not be taking N3. What is the valency will be taking over here. So that formula crisscross will be applied over here. Right? Second, with the reaction, dinitrogen reaction with oxygen. Second reaction. So dinitrogen is N2 and O2, which reacts with the high temperature. We say 2000 Kelvin temperature. It's a high temperature. At this temperature, we say nitric acid will be produced. Very important reaction it is. So nitric oxide forms when dinitrogen combined with the dioxygen at very high temperature. Okay. So we are done with the dinitrogen. Let's do ammonia. Next compound of nitrogen, ammonia. So let me tell you, it's a most important Haber's process we have over here. I'll make you to learn very easy way. Second compound we are learning. Ammonia, we have the lab preparation, and then we have, so this is a pungent smelling gas, okay? And basically from decay of nitrogenous organic matter like urea, it will produce the ammonia. So when we take urea, suppose NH2CONH2, this is the first organic compound, artificially made organic compound actually. When this hydrolyzed, correct, because decomposition is taking place, so it gives the ammonium carbonate, and then ammonium carbonate will be uh, going for the decomposition and gives the ammonia plus water and plus carbon dioxide. Okay, so this reaction is general, like in a soil it happens because we use urea as the fertilizer, correct? Urea as a fertilizer, so it reacts, and this is how it in the soil or the reaction happens. Okay, then lab preparation, in this can happen even in lab also. Specifically if they ask for the lab preparation, what to be written, what reaction to be written, remember lab preparation ke liye we are having sodium, like you have seen, magnesium nitride, barium nitride, calcium nitride. Those reaction can happen with the hot water, so that produces uh, uh, we can say hydroxides of the respective metals. Magnesium liya to magnesium hydroxide and ammonia will be formed. Okay, then other way we can have with the salt, like let me tell you, ammonium chloride even has a reaction with the calcium hydroxide alkali compound, and this gives out ammonia plus water, and it gives the calcium chloride salt. So let us balance the reaction. 2 moles over here needed H2O. Okay, balanced. Now the second one we can have even with the ammonium sulfate. This is also the ammonia salt, but ammonium nitrate cannot be taken because ammonium nitrate is explosive. So we have seen in the two salts of the ammonia, ammonium chloride and ammonium sulfate, treating with the alkali. The first we have taken COH, second time we are taking NaOH. So we mostly avoid with NaOH because it is hygroscopic in nature, and caustic soda it is, right, hygroscopic in nature. So very difficult to remove them. Ask Papa. Papa will help you.
आप बनाते हैं आप लड़की इसलिए आप बनाएंगे लड़की है आप लड़की है आप लड़की है लड़की 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 और चाहिए मम्मी अब ये तो नहीं
Raghu, please, you are disturbing my class. Oh, Papa will help you. Papa will help you, beta. Papa will help. Take it, take it. So now we can see here ammonium sulfate NaOH gives the ammonia plus H2O and plus sodium sulfate. So ammonium sulfate with the alkali, whenever it reacts, ammonium salt with alkali, it liberates the ammonia gas. Both the reaction, these are the laboratory reactions. Okay. Now balancing, I hope we are done with the number of 2 Na ammonia, NH4 here, 8 hydrogen, 3 over here and 4 over here. So this is not balanced. I hope 2 moles needed. Yeah, balanced. This is laboratory preparation. Industrial preparation, if we are manufacturing ammonia by industrial process, so we have the process name that is called the Haber's process. Haber's process based on, some Laissez-faire principles. So here the rule will be followed and reaction will be carried over here. Nitrogen gas, hydrogen gas, 3 moles will be combining and forming 2 moles of ammonia gas. Okay, so during this process, what you need to remember is some conditions. What are the conditions we have to follow? That's very important. If we do not follow that condition, the reaction may proceed to forward or backward instead of that. Okay, so we can have a Laissez-faire principle for this. That is the first most important, high pressure. The first thing, we need to maintain the high pressure because gases are getting compressed. So high pressure is the favorable condition. Remember, for the preparation of ammonia, this is the favorable condition. So how much pressure should be taken? 200 to 300 atmosphere, sorry, 900. That much pressure can be maintained. Then second, low temperature. Temperature should not be very much increased because then we can say plant will not work, manufacture plant will not work. So low pressure temperature is a favorable because formation of ammonia is exothermic process. Formation of ammonia is exothermic reaction. So how it, because heat comes out in a form of negative. So it is exothermic reaction. Did you understand? Kilojoule per mole. So reason also I have specified over here. So remember, why do we need low temperature? I have mentioned the reason here itself. Then iron oxide is used as catalyst. Okay, and potassium, we can say oxide, and aluminium oxide are used as promoter. What is the function of promoter? To enhance the activity of the catalyst. That's all. Okay, so before, what was used? Instead of iron oxide, what was used? Iron. Okay, and instead of this potassium oxide and aluminium oxide, what was used? Molybdenum as the promoter. Did you understand? So it was used before, but now what they are using is iron oxide as the catalyst and potassium oxide as a promoter. Did you understand? So this is the reaction taken place over here. Let me teach you in a simple three-step process how the reaction takes place. So we say the compression chamber, gases will be sent. So compression first, and in the compression we will take the one volume nitrogen gas and three volume hydrogen gas in a compression chamber at high pressure. Okay, gases are compressed, and after compression it will be sent into a catalytic chamber. Catalytic chamber is made up of iron oxide. यहाँ पे लिख जाओ, यहाँ पे नहीं सर में छोड़ दो. Okay, so catalytic chamber is made up of iron oxide, where these compressed gases, nitrogen and hydrogen gases, 1:3 volume, combining and forming ammonia. So this happens in the presence of iron oxide, right? This is catalytic chamber where we have potassium oxide and aluminium oxide as the promoter. Okay, temperature must be kept low, not high. 450 to 500, it is enough temperature for preparing ammonia. Okay, Hridaya?
Yes, ma'am.
Hridaya, are you understanding? Okay, after this, we will be sending it for the cooling. Okay, cooling process. So these gases which are prepared over here, ammonia form, it will be collected in a liquid ammonia. It will be collected in a liquid ammonia after cooling. So liquid ammonia, how it will be represented? NH4OH. What is liquid ammonia? NH4OH form. Unreacted gases, unreacted, which is not reacted, unreacted nitrogen and hydrogen gases are recycled. Okay, so no need to learn the whole diagram. There is a flow chart or flow diagram or just a diagram, ray diagram, which is called as a line diagram. That helps us to know the chamber. So basically, I ask children to prepare this whole process by learning CQ. What do you mean by CQ? First C means compression, second C means catalytic chamber reaction, catalytic oxidation, basically the chamber reaction, what is happening. And third is the cooling process. Did you understand the 3C meaning? What do you mean by 3C? So Haber's process is based on 3C process. The first is the compression. One volume nitrogen and three volume hydrogen are compressed at high pressure. After compressing, these gases are sent to the catalytic chamber where we have catalyst iron oxide, promoter, we are having present potassium oxide and aluminum oxide at temperature, we can say 450 to 500. Pressure we have already used in the first chamber itself. Then it has to be sent for the cooling. Once reaction happens, nitrogen and hydrogens are combined, right, will produce the ammonia. So it will be sent in a cooling chamber. And then once it gets cooled, it will be collected in a liquid ammonia form, that is ammonium hydroxide. Unreacted gas, where we have some gases are not getting reacted, right? Definitely some unreacted part will be left. Those gases will be sent back and recycled, right? Did you understand, Hridaya? And the last structure I would teach, and then I'll wind up the class today. Today's class I'll finish. Ammonia structure. So NH3 lone pair we are going to learn. Basically, nitrogen, 3 electrons. This is as per the same number of availability of electrons. It looks like it is a tetrahedral shape. But what we see over here is what we see over here is a bond pair and lone pair repulsion takes place. What do you call this as the bond pair? Nitrogen. Ask Papa, na baby, I am busy. Nitrogen and hydrogen we are having as the bond pair. So how many bond pairs we have? 3, correct? So 3 nitrogen hydrogen we can have bond pair and 1 lone pair present. Can you see the lone pair? 1 lone pair present. So due to, we can say, lone pair and bond pair repulsors, there will be push among this. There will be slight repulsions between them. So that angle will be distorted. It is expected to show the tetrahedral shape. Expected to show the tetrahedral shape, but it is not showing the tetrahedral shape. What is the reason behind it? We are having lone pair and bond pair repulsion, due to which angle distorted. So look at over here the structure. It comes now 100. 107 to 5 degree, the nitrogen. So basically they go to the different shape. What do you call the shape as the pyramidal shape? It does not come to tetrahedral. So why it has, because it looks like the sp3. We have one s orbital, 3p orbital hybridization. So overlapping, it gives the sp3 hybridization. Seeing sp3 hybridization, we can say it may go for tetrahedral, but it does not go for tetrahedral shape. What the shape is, it's seen in this molecule, gives the trigonal pyramidal shape. It gives the trigonal pyramidal shape. Why is that so? Why not tetrahedral shape has come? So the reason is angle slightly less. It becomes distorted. Angle distorted, you can see. Angle distorted from how much? 109 degree 28 minutes, right, to 107.5 degree. Okay, so the actual shape is pyramidal, not tetrahedral, trigonal pyramidal. Did you understand? So this Angle distortion is basically, we say, due to repulsion. And where does the repulsion take place? Between lone pair and bond pair. Did you understand? What do you mean by LP and BP? Lone pair, bond pair. Okay, so this repulsion pushes the angle and get distorted from 109 to 107. This is most important thing that we need to say. The reason behind it is the lone pair bond pair repulsion. So we are basically done with two components of the nitrogen. One is dinitrogen. You have seen the dinitrogen structure, the bond existing between the nitrogen and the preparation of properties of dinitrogen. And we have done the ammonia. Correct? Preparation, till the preparation. Okay? And the structure also. So basically, the chapter will be over very quickly, not a very difficult part, as I said. A very important chapter. Most of the things you have to do from your side because remembering many compounds, structure, formula, right? All these things are there. Okay, Hridaya?
Yes, ma'am.
Yeah. So see you tomorrow. But the tomorrow's class, please note, you will be joining at 3:30 p.m. tomorrow. To remember because I'm joining tomorrow school. So I'll come at 3 o'clock. Okay.
Ma'am, tomorrow and day after, I don't think I'll be able to come because I have my French viva.
You have French
Yes, ma'am. My
exams. So
yes,
when are you joining? Back
third.
on third. Third
Yes,
day will be Friday.
yes, ma'am.
Okay. Okay, Hridaya, no worries. If in case in the evening you are available, please let me know.
Yes, ma'am.
Okay.